Hi everyone. In this section on wave optics, we're going to again consider light as a wave. The wave model of light is really useful here because it explains diffraction and interference of light, which leads to some interesting optical effects. So light as a wave is an electromagnetic wave, which is created by oscillating electric and magnetic fields and transports energy through space. So electromagnetic waves are really a form of energy that can move through space and again do not require a medium to propagate. So electromagnetic radiation is classified on the electromagnetic spectrum, and it's usually, it is organized by its frequency and its wavelength. So at the high end of the spectrum, we have X-rays and gamma rays, which have high frequency and high energy. And then at the low end, there's radio waves, which have low frequency and low energy. Near the middle, there's a region of electromagnetic radiation called visible light, and our eyes are tuned to see light within this specific range of frequencies. So there's really no difference between visible light and X-rays or gamma rays or radio waves or UV light, other than that our eyes are tuned to see that frequency. Okay, let's look again at the superposition of waves leading to constructive and destructive interference. This applies to any waves, doesn't have to be specifically light. So for now, let's consider two sinusoidal wave sources that are coherent. Coherent means they're emitting waves that are in phase. And superposition tells us that when those waves overlap, the resulting wave displacement will be equal to the algebraic sum of the two individual wave displacements. So if we have these two sources here, S1 and S2, if I choose any point in space, such as here, R1 is the distance to that point from S1, and R2 is the distance from that point to S2. So delta R here is called the path difference. It's the difference that the waves travel as they leave source 2 from source 1 by the time they reach this point. So we have delta R equals R2 minus R1. Constructive interference will occur at points where the path difference is equal to an integer multiple of the wavelength. This essentially means that two crests are meeting at that point and adding to produce a wave of larger amplitude. So for maximum constructive interference, generally we'll just say constructive interference, we have delta R equals m lambda, and m is an integer, so 0, plus or minus 1, plus or minus 2. Similarly, for points of destructive interference, we have delta R equals m plus a half lambda. So our maximum destructive interference will occur at points where the waves meet with a path difference of a half wavelength. So m again is the same integer, and this time we're getting that half wavelength difference. And this will cancel completely if the amplitudes of the waves are the same. In that case, we'll have a zero displacement at that point. If we were to connect all the points in space where there was constructive interference, we would have a curve, and this is called an antinodal curve. If we connect all the points where there's destructive interference, that would be called a nodal curve. And these are the same terms that we use for standing waves. Example 1, two speakers are driven by the same oscillator of frequency 200 Hz. They are located on a vertical pole 4 meters apart. A man stands far away from the pole with his ear at the level of the lower speaker. How many minima in sound intensity will he hear as he walks towards the pole, and where will these be located? Assume that there are no reflections from the ground. Okay, so the setup looks like this. I've drawn it again and added in this line here. So these are the two sources. This could be 1 and this is 2. So we have R1, the distance to the point. The point is where the person is standing. And then R2, the distance from the point to speaker 2. And this is a right triangle. And then we have the separation of the speakers, which is 4 meters. So we will need to find the wavelength of the sound. So lambda equals V over F. We can use the speed of sound in air, 343 meters per second. That is at 20 degrees, technically, over 200 Hertz. So 1.72 meters. Okay, and then we're looking for the minima. So these are the points where he hears no sound. It will be along this line. So our unknown will be the R1 values. where there's destructive interference. So the minima are at delta R equals m plus a half lambda. So we can check if we were going to plug in a few delta R values. For example, if I plug in 0, then I have 1/2 lambda, which is 1.72 divided by 2, so 0.86 meters. And then if I kept going, I would have, so plugging in 1, giving 3/2 lambda is 2.58 meters. And then m equals 2 gives 4.30 meters. And 6.02, and then we could keep going. So I'm only using positive integers because the person is walking towards the speaker, so it is only in that one direction, which we'll call the positive direction. Okay, let's look at this triangle. So this is a right angle triangle here, so this gives us some restrictions that we can use. Since it's a right angle triangle, we have Pythagorean theorem first, so r2 squared, the hypotenuse, will be d squared plus r1 squared, so adding the two sides. And then I could solve here for r2. It would be the root of d squared plus r1 squared. And then we also know that r2 is the hypotenuse, so we have to have r2 less than 4 meters plus r1, or d plus r1. Okay, and now if I just move this around, this is r2 minus r1 is less than d, or less than 4, which means that we can restrict r2 minus r1 as delta r. So we can see that we can't have 4.3 meters or 6.2 because they're over 4. So our only options for the path difference are 0.86 meters and 2.58 meters. So now let's take that and go back to our path difference formula. So r2 minus r1 equals delta r, moving that up. And I want to plug in so that this is just an equation in terms of r1. So let's plug in here for r2 right here. So we'll have the root of d squared plus r1 squared minus r1 equals delta r. And that's really it. So what I'm going to do is solve for r1 here. And then we can plug in, we'll get two answers, one when we plug in delta r is 0.86 meters, and one when we put 2.58 meters. Okay, so I'll get this root by itself on one side, delta r plus r1, and I'm just going to turn the page. Okay, now I want to solve for r1, so I'm going to have to square both sides. So we have d squared plus r1 squared equals delta r squared plus 2 delta r r1 plus r1 squared. And we don't need a quadratic because r1 cancels, so that's nice. And then I can solve for r1 here. So we'll have r1 equals d squared minus delta r squared over 2 delta r. And then again, I'm going to plug in delta r is 0.86 and 2.58. Okay. So we'll have r1, one solution is 4 meters squared minus 0.86 meters squared over 2 times 0.86 meters. And that one gives me, let's see, 8.87 meters. And the second, r1, I can plug in 2.58. So r1 is 4 meters squared minus 2.58 meters over 2 times 2.58, and this time we get 1.81. Okay, so as the person walks towards the speaker, they will hear two minima, one at 1.81 meters and the other at 8.87 meters. Young's double slit experiment is one of the first experiments that showed the wave nature of light. It also has very important implications in quantum mechanics. So it turns out that it's very difficult to place two coherent light sources next to each other. So instead, we can take one light source and then split it into two separate light sources. Young first did this in 1801 with sunlight, but we can understand this as well with a laser. So you can imagine a laser that's incident on a screen that contains two narrow slits that are very close together. So this is exaggerated, they're very close together. And that splits the light essentially into two sources. So these waves spread out from this point due to diffraction, and then they overlap, and what results is interference. And if there's another screen placed a distance away from the double slit, what we'll see is interference fringes on the screen. In the center, directly perpendicular to the double slit apparatus, will be a bright central maximum, and that's labeled m equals 0. Then moving up or down from that point, we'll have bright fringes, which is where constructive interference occurs, and dark fringes. And each one is labeled with an integer from this point. So above we'll have m equals 1 for the first bright fringe, and then it would be m equals 2, and below that line we'd have m equals -1, and then -2 to label the lower fringes. Okay, let's look at the math for this apparatus. Okay, so we have the Young's double slit apparatus here, and then the interference pattern is viewed on a distant screen. So it looks something like this. Y equals 0 is the vertical position of the central maximum, which is on a screen a distance L from the double slit, and then theta is the angle to the light where it reaches the screen at point P, a distance Y or a vertical position Y above the central maximum. So we're assuming again that L is much greater than D, much greater, so that the screen is very distant. And the slit separation is generally very small. So, all right, so it looks something like this if we consider the light rays coming from two different slits here. And since the screen is so distant, we can assume that the light rays are nearly parallel. Essentially parallel, but also it's nearly parallel so that they do meet at a point on this distant screen. Okay, so if the light rays are at angle theta, then we can also draw this perpendicular line here that intersects this light ray at a right angle. This angle would be theta as well, and then our path difference is given by delta r equals d sine theta. When the waves meet at point P, there is constructive interference if the path difference, again, is an integer multiple of the wavelength. And we know this is d sine theta. So now we have d sine theta equals m lambda. Often, especially for light, we're going to apply the small angle approximation, and this is valid as long as we have lambda much less than d. You can see why that would make theta very small. And in that case, theta is equal to sine theta approximately, so we have theta equals m lambda over d. This expression will give the angles at which the constructive interference fringes occur, but often we want to find the vertical position as well. So we have y equals L tan theta, and we can again use the small angle approximation. This time for tan theta, we have that equal to theta as well. So theta equals y over L, and it's m lambda over d, and solving for y gives us m lambda L over d, where m is 0 plus or minus 1 plus or minus 2, and this gives the vertical position of the constructive interference fringes. Since the interference pattern is a series of equally spaced fringes, we can also find the fringe spacing by subtracting the vertical positions of two adjacent fringes. So to do this, we have delta y equals y. I'll just call this m plus 1 minus y of m. So m plus 1 lambda L over d minus m lambda L over d. Subtracting these, the m's cancel and we end up with lambda L over d. And this gives the fringe spacing. So you can see it depends on the wavelength and the length. The length was the distance between the double slit apparatus and the screen. And then it's inversely proportional to the separation between the slits. Okay, again, these are all length measurements, so just make sure that you have the same unit for all of them. Then I could write the same theory that I wrote out previously for the destructive interference points, which produce dark fringes, but now they occur at points where the path difference between the waves coming from each slit is equal to half a wavelength. So we would have m plus a half wavelength here instead of m. So these are the vertical positions for the dark fringes. I've just written this out again to summarize. So to summarize, for the bright fringes, the position is y equals ml are m lambda L over d, or we could find the angles using d sine theta equals m lambda. And the dark fringes are at y equals m plus a half lambda L over d, and d sine theta is m plus a half lambda. And m in both of these cases is 0, plus or minus 1, plus or minus 2, and so on. Okay, let's do the first example. Example 2, a monochromatic beam of light impinges on Young's double slit experiment in which the slits are separated by 0.2 millimeters and are located 1 meter from the screen. The m equals 3 bright fringe is located 9.49 millimeters from the central fringe. Find the wavelength of the light. Monochromatic means that this is light of a single frequency, like a laser, opposed to white light that has multiple frequencies. Okay, so we have y equals m lambda L over d. Since we're looking at the m equals 3 bright fringe, and we have y, so we can really just rearrange here for lambda, which will be dy over ml. So I'm going to put everything into meters, 0.2 times 10 to the negative 3 meters times 9.49 times 10 to the negative 3 meters over m, which is 3 times L, which was 1 meter, gives me 6.33 times 10 to the negative 7 meters. So this is 633 times 10 to the negative 9 meters, or 633 nanometers. Often for light, especially visible light, we'll express the wavelength in nanometers, but of course this is correct as well in proper scientific notation. Example 3, light of wavelength 600 nanometers illuminates a double slit. The intensity pattern shown in the figure is seen on a screen 2 meters behind the slits. A, what is the spacing between the slits? B, if the entire apparatus was immersed in water, how would the spacing between the bright fringes change? Alright, so I've drawn out just a small portion of the diagram. There's more than one way to read information off of this. To me, it looks most obvious maybe to use the y equals 1 position. You could use the fringe spacing instead. Okay, so if this is 0, we know that, 1 centimeter is here, which is m equals 0, 1, 2, and 3. So this is the m equals 3 bright fringe. It's bright because of the high intensity here. So y3 is 1 centimeter. Wavelength, we have 600 nanometers. And then y is Lm lambda over d. We can solve for d, so d equals Lm lambda over y. And just plug in the values here. So that's 2 meters times 3 times 600 times 10 to the negative 9 meters over y, 1 times 10 to the negative 2 meters, which gives 3.6 times 10 to the negative 3 meters. So then part B is interesting. It's if we take this whole setup or the double slit apparatus and put it into water, what changes and how does that affect the fringe spacing? So our fringe spacing delta y is lambda L over d. The only thing that changes here is the wavelength. This changes when it's brought into water because of the change in the speed of light in the water. We know v is c over n, and this equals lambda f. F will still be constant. That's always equal in a sense to the source frequency. So we have wavelength proportional to 1 over n. So this means that lambda in water will be lambda in air over 1.33. So if you do 1 over 1.33, this is 0.75 lambda in air. And we see from this relationship that the fringe spacing delta y is proportional to the wavelength. So it will also reduce, so it's going to decrease by a factor of 0.75. So the fringe spacing decreases by the same factor as the wavelength. A laser beam with a wavelength of 524 nanometers is exactly perpendicular to a screen having 2 narrow slits spaced 0.15 millimeters apart. Interference fringes, including a central maximum, are observed on a viewing screen 1 meter away. The laser beam is then slowly rotated by 1 degree about an axis parallel to the slits until it makes an 89-degree angle with the screen. How far does the central maximum move on the screen? Okay, despite all of the wording, this is actually a simple example. So we have the laser here. If it was perpendicular to the screen, then we would have a central maximum here. Now when we shift it by 1 degree here so that it makes 89 degrees with the screen, as the question says, now we have a 1 degree angle shift between that position. So delta y in a sense here is that shift of the central maximum. So I'm just going to use this setup to find delta y because we have a right angle triangle here. So we'll have tan theta equals delta y over L. So delta y is L tan theta, which is 1 meter tan of 1 degree, so 0.0175 meters. So notice in this theoretical model, we have all of the interference fringes at the same intensity. In fact, in a real setup, what happens is that the bright central fringe is the brightest antinodal line, and then from there the intensity falls off. So we'll see why this happens as we look at the single slit experiment.